Hi, everyone. Thank you for joining today's webinar. Today, we will be covering the FactSage API within METSIM. If you have any questions over this regarding FactSage or the API, please see my contact details on the last slide, along with details on our upcoming webinars and training courses. Also, please follow us on LinkedIn for all of the latest METSIM news. So the agenda for today's webinar is first to give an introduction to FactSage, and this will be provided by Jean-Philippe Harvey over at FactSage. Then after that, we'll be getting into the FactSage API within METSIM, followed by a case study where then I'll discuss a application of how you can use FactSage, and we'll look at a matrix model that has been created using lab, test work, and published data, and compare that to the equilibrium prediction by FactSage. Now I will pass it over to JP.
Thank you, Dylan. So before starting looking at the API between FactSage and METSIM, we thought it would be important to explain a little bit about FactSage, what it is exactly. So I will take the next 5 minutes to explain this software. So you can see here on the left the interface of FactSage. So it is a tool that is used to perform complex equilibrium calculation. So this is a computational thermodynamic software, like I mentioned, that will calculate equilibrium state of different type of multi-component and multiphasic system. In the back end of that, you have a calculation engine which will evaluate the phase assemblage for different set of constraints by doing the minimization of the Gibbs energy of a system. And what is unique and really where the strength relies between this connection with FactSage and METSIM is the unique thermodynamic databases that we have developed over the year, which contain information about the energetic behavior of important and critical phases for the modeling of pyrometallurgical operation, such as slag, matte, molten salt, and molten metal, as well as different solid phases, which are needed to model alloys. Next. So basically, what you can do with the interface are manifold. So you can see here on the left, single point calculation for an aluminum alloy. So basically you have a graphical interface and you can input your mass balance, temperature and pressure, and as an output obtain useful information about phase assemblage and other information about state properties such as Gibbs energy, enthalpy, entropy, so on and so forth. So this is what you would get from the interface. And another important type of calculation that you can do with FactSage are the generation of phase diagram, which is kind of the most important tool for a metallurgist when they're looking at a process and they want to design, for example, a unit operation where they want to target a specific temperature above which all the system would be in a liquid state. Next. So finally, and that will be the topic of today's webinar, really the important item here is to use the strength of our databases to model pyrometallurgical operation via the API that we're going to present. And what you can see here on the left is a list of the different proprietary databases that have been developed over the past 20 to 30 years here in FactSage. So you have database to describe oxide, salt, sulfide, so on and so forth. And the idea now is to embed these calculations into the process simulation tool that is METSIM to provide to customer, let's say, the possibility to explore the behavior of pyrometallurgical unit operation. So in about 5 minutes, this will be the introduction that I wanted to present for FactSage. So back to you, Dylan.
Thank you, JP. So now let's talk a little bit more about the API within METSIM. So in order to use this, you'll need to have a FactSage license along with the METSIM heat balance module. If you have any questions over that, just feel free to reach out to me. The benefits of using the FactSage API is first, as JP discussed, the access to their thermodynamic database for thousands of compounds and solutions of the metals, liquid, and solid oxide solutions, math, molten, and solids. The calculation of conditions for multi-phase and multi-component equilibria, and the complex heat balance is allow for an accurate equipment design. Some limitations of this is it assumes perfect mixing and equilibrium. So this is a tool that you can use for an operational goal. So the goal of METSIM and the API is to build a complete process simulation and produce accurate mass and energy balances, to verify and compare test work and published data to equilibrium results, as we'll be showing through this presentation, and to reduce the time, effort, and money spent during the test work stages and development of a project. So we're going to start off with a two flow sheet model. This first flow sheet with a direct reduction of iron. We see our feed, which is going to be our feed ore, primarily hematite with some moostite, magnetite, and gangue in stream 101. We have some water entering for cooling the gas, some fuel gas that we have a few different injection points, and some air that's being controlled in order to have enough oxygen for our combustion reactions. Then we see our furnaces broken down into 3 stages, so we can get an accurate chemistry for each stage. We take a look at the electric arc furnace. Stream 401 is our heated air. We have a pure oxygen control in stream 402. Our flux being added, which in this case it's 95% lime. Our carbon source. And finally, our iron components coming from our furnace at a discharge temperature of 675 C. So now let's take a step back and look at the thermo data that can be input for each component within METSIM. So if you're familiar with METSIM, you've seen the screen multiple times where we have our component tab that'll have the chemical formula, the name, the phase, and some of the other properties. Then in our thermo tab, we have our reference to where this thermo data was taken. We have, I'll just cover kind of some of the major ones. The temperature range for that component thermo data is valid. We have our heat of formation. This is very important for reaction chemistry. Then our enthalpy coefficients, and this is where the stream heat contents are calculated from down here. And within METSIM, we can produce a heat balance summary. So this is the first table that you'll see if you go into your heat balance summary, where it shows you which units you're in. In this case, it's 1,000 kilocalories per hour. We have 7 different heat balance columns. Over on the left, we see this is all of the different unit operations within this model. And on the right is the balance. So if all of these streams and heat contents balance to 0, that is the goal. You do not want to see any values here or any significant values here, as that means there is likely an error in the heat balance and something needs to be fixed or modified. So our input stream and our output stream are pretty similar. Those are the stream heat contents of each individual stream going into the unit op, and I'll show a table here in a couple of slides that involves that. We have our heat of reaction, and the next slide I'll go into a little bit more detail on this. Our heat of solution, this is the heat of mixture of aqueous components, so acid to water. You can track your heat of mixing as you're going throughout your entire model. The energy input and heat lost, this can be calculated or specified by the user and input into each unit op directly. Your heat required, this will be if you're setting a temperature in a discharge stream or somewhere in METSIM where you're forcing it to a certain temperature, it'll tell you the amount of heat that either needs to be added or removed in order to hit that set point. Our next slide is the heat of reaction breakdown. So on the previous slide, we saw the total number for each unit op. Now we see the chemistry that is for each reaction that is going into each unit op. So over here, we see our unit op number and all of the reactions that are happening in that unit op. We see our formula, so our reaction chemistry on a per mole basis and a total basis. So the heat of reaction is calculated for every reaction within METSIM, and it's calculated from the heat of formation, so your reactants minus your products, and your molar flow rate in your feed streams. Then lastly, the stream heat content. This is calculated from the enthalpies of all of the components within a stream going into the unit op, and it's associated with the mass flow rate. And you can see the three different units that we have here. Now I'll go through a demo of getting all of this set up. So let me get that started. So let's compare a model that has been built using the traditional approach, using test work and published data, to the equilibrium results produced by FactSage. We see our component list over here, and that's the traditional list you would build with any METSIM model. We've broken down the furnace into 3 different stages, and for this traditional approach, we put in the chemistry for each one of the stages along with the reaction extent, and that is generally what requires the most work and effort, is getting an accurate representation of the chemistry and an extent of reaction. We have a Gibbs-free energy minimization unit operation in METSIM, which calculates the chemical equilibrium based off minimizing the Gibbs-free energy. Note this is slightly limited in the information and databases that it's pulling from, which is the purpose of having that FactSage tool, that they have that extensive database. But here you can put in the equilibrium temperature and pressure and run the model, and it will predict the chemistry. So if we look at our input, we can look at our temperature, our composition of the gas, along with our flow rates. Then going into our reduction agent and gas, we see we have our carbon monoxide as our reduction agent, about 141 tons per hour going into the furnace. And we could also look at our metal product. Here we see we have a slight amount of carbon coming out with our iron product, about 2.5 tons. So now we're going to compare this to what is predicted by FactSage. And the first step is to make a CST file from the components in the METSIM model. And once we turn on FactSage, we will then select this file that we create here. You can choose where the source for the thermo data is coming from. In this case, the METS just says that we're going to be using the heat of formation from METSIM, but for each component, you have the option to choose the different sources. So we can see the newly created CST file. Then in our model parameters and external interfaces, this is where we turn on the FactSage API. And once we press OK or exited out of that window, we'll then be asked to select the CST file we want to use. And looking at our components now, we'll see the new name based off the FactSage name of each one of our components. And if we open up one of these, the reference is now FS for FactSage, and we see the only value that wasn't replaced with a 0, as everything else will be done in FactSage, is the heat of formation, and we'll be using the value that was put into METSIM, as we chose that METS source. And now this is the pre-calculated values, and if we use this fact button, we can see if that stream is at equilibrium or not. So this is telling us that it is not at equilibrium according to the FactSage calculations. So here we see about a 20 ton per hour difference in our reducing agent, which can be pretty important. And once FactSage is turned on, then the FEM unit op will be calculating based off FactSage calculations. So it's still going to look at your equilibrium temperature and pressure. Then when we calculate this, you'll see that this will take a little bit longer, as we're going from a tolerance range of 0.2 to 0 or 1 e to the negative 6. And you can reduce kind of the back and forth time by tightening that tolerance range. But now when we look at our feed stream going into the furnace, for the gas, we can verify that this is now at equilibrium. So we have our matching tonnages for different components. And our stream enthalpy. And another thing you can do within METSIM is do a direct comparison. So here we see the electric arc furnace with all of the reaction chemistry, and that is matching the published and test work data. And what we're going to do is now add a FEM unit op to do a side-by-side comparison. So we have 5 input streams coming in here. So now we're going to add 5 input streams to this unit op along with our 3 discharge streams. I'm going to copy all of that stream info. So you see all of that stream info was checked, and we'll just copy it from stream to stream. For all of our inputs. And in that FEM, we'll put in the equilibrium temperature and the pressure. And here we'll let FactSage do all the equilibrium calculations. So now if we specify which unit op we want to run and tighten that tolerance range, you should see this will solve much faster, in about 4 to 5 seconds. The first run that we calculate, it's putting everything into one stream. So we need to specify where each phase is going, or what stream each phase is going to. And we can do that with the mass splits in the FEM unit op. where we have our gas and solids going to different locations. Once we rerun that unit op, we now see that stream 78 is our off gas, 77 is the slag, and 76 is the metal product. We now take a look at the metal product that's based off the equilibrium calculations. We see that that is a pure iron, while in the metal product for the test work and published data, we see that we have about 1.4% carbon. We look at the slag and the test work data, we see that there's about 2% iron oxide being formed. If we look at the equilibrium data, we don't see any of this that is predicted to form. And we also see our carbon that is dropping out in the solids phase instead of with the metal product. And lastly, if we look at the gas discharge, here we have about 19 tenths per hour of carbon monoxide. But if we look at our test work, we see a reduced amount of carbon monoxide, and we also see some unreacted oxygen. So we can see some inefficiencies there. And in summary, if we look at kind of the results side by side, if we look at the METSIM approach that's based off test work and published data, we see about 20 tons per hour more carbon monoxide that is going into of our reducing agent that's going into the furnace. We see in the electric arc furnace that in the molten there was about 1.3% of the product being carbon, while the equilibrium results did not predict any. There's about 2% of iron oxide produced in the slag, where the equilibrium results do not predict any iron oxide being formed, and the carbon also being shown in the solids phase. Then the test work data also shows about 10% by volume of unreacted oxygen, while the equilibrium does not predict any unreacted oxygen. So in conclusion, the data pulled from the test work and published sources does not fully match the equilibrium data calculated by FactSage. And FactSage assumes complete mixing and equilibrium. So that gives us a tool for an operational goal for any type of pyrometallurgical process. So further modeling will need to be done along with some analysis and operational expertise in order to achieve a closer match between this data and the equilibrium data. So for the next steps, the first is to determine if the iron reduction can even be achieved with the lower flow rate of the reduction agent shown by the equilibrium calculations, so that 20 ton per hour difference of carbon monoxide. Then lastly, process modeling to determine optimal flotation conditions, followed by test work confirmation. So that is it for today's webinar. Thank you everyone for joining. And if you have any questions, absolutely feel free to reach out to me. And go to our website under the Training and Resources tab for all upcoming webinars, public training courses, and tutorial videos. Thank you.